Okay, the tau d is obtained from the calculation. This block continuously adjusts the control signal to minimize the error. The PID output then goes to a block that models the both with the transfer function, as we can see, the 0.106 over first for s plus 1. This means the valve doesn't respond instantly, but rather as a first order system with a time constant of 4 seconds. After that, we have the plant block. This block is the most important, which represents the main process. In this case, it is modeled at, as a first order system with a gain of 2.5 and the time constant of 10 seconds expressed as a 2.5 over 10 seconds s 10s plus 1. We can also add the disturbance block with a transfer function as a 0.9 over 5s plus 1. This block helps test to the robustness of the controller, since the real process will always suggest the disturbance that affects the controller variable. Finally, the plant output is measured through a transmitter with a gain of 0.4. This signal goes back to the comparator closing the control loop. With the Simulink model, we observe the dynamic behavior of the system with the change are applied to the set point or when a center disturbance occurs, and evaluate the effectiveness of the SIMC controller. After that, we can see the PID and SIMC calculation. Right now, in this slide, we can see the main process. This one is a transfer function about the process. So we have the first case, as we saw in the book. This one is this model. This one is this model. So we just can take the values from the main process. This one is the transfer function, and we use the tau one. In this case, tau one is equal 10. Tau two is equal 4, and this value 10 0.106 is k. This one is multiplying the tau 3s plus 1. But after that, we can calculate the multiplication about kc and multiply for k. The k is the value that we have. Okay, and also how to calculate the kc, we use that formula with all the values that we have. And remember, we have to use a theta plot. Theta is 1 to make the calculation easier. Also, after that, we have the tau sub e, and we calculated in this case tau 1 plus tau 2 minus tau 3, and we use this, and also we can use this formula to get it. And the last one is a tau d. Tau d, we use this formula. We have tau 1 and tau 2, so we just use the value that we have. Okay, what about this representation? The representation, finally, the slides shows the comparison between the classical Ziegler-Nichols tuning method and SIMC. The curve for Ziegler-Nichols shows a response with a high overshoot, meaning the control variable exceeds the set point significantly before settling down. And it also exhibits oscillation that take times to dampen, which in real process can be risk, as it may compromise stability and even damage equipment or product quality. On the other hand, the SIMC method provides much more stable and controlled response. While it may look slightly slower at the beginning, and it reach the set point with minimal overshoot and really robustness against disturbance. This means the SIMC achieved a balance between the speed and stability, making it more suitable in industrial process with dead time and complex dynamics, such as a time system we model. In conclusion, while Ziegler Nichols aim for the fast response, SIMC prioritize stability and reliability, offering safer and more practical performance and real application.